Okay, so for this video, we're going to look at a bigger version of the circular motion. Rather than just small scale like we did in the previous videos, this one's going to be about looking at planets and stars. So we're going to look at what's called Kepler's laws of motion. We're going to look at something called eccentricity, and then we're going to look at orbital speed and period. So again, for planets and stars. So a guy named Johannes Kepler, after doing many observations, came up with 3 laws of planetary motion. The first law is that planets travel around a star in an elliptical orbit, and the star, or in our case, the sun, is at one of the focal points. So an ellipse, if you remember from math class, an ellipse is an object that has 2 focal points and an area sweeps around it. The second law says that an imaginary line drawn from the sun to any planet sweeps out equal areas in equal amounts of time intervals. That also indicates why some planets have faster and slower orbits at certain points. And the third law is the square of each planet's orbital period is proportional to the cube of the distance between the planet and the sun. Now we're going to go into these in more detail on this video. So the first law talks about the planets orbiting a star in an ellipse. And when we look at how oval-shaped an orbit is, we look at something called the eccentricity, which looks at how oval-shaped the orbit is. An eccentricity of 0 means the orbit is a perfect circle, and what happens there is the foci, the focal points, are at one spot in the middle. Okay, so the formula for eccentricity is the distance between the focal points, so the difference between the foci, and the major axis. And as you see, the major axis is always bigger than the distance between the focal points. So the eccentricities is always less than 1. So for example, if the difference between your foci is what are called astronomical units. 1 astronomical unit is the distance between the Earth and the Sun. So let's say the foci is 2, and the major axis is 6. So 2 divided by 6 is a third. So 0.3 would be your eccentricity. So the greater the distance between the foci and the major axes, the greater your eccentricity. So just examples here. Perfect circle eccentricity of 0. It gets a little bit longer. It's 0.2, 0.5, 0.8, 0.9, 0.95. If it gets to be an eccentricity of 1, it's basically a line. Okay, and here are the eccentricities of planets of the solar system. Notice Mercury and Pluto have the biggest eccentricities. They're the most. Venus and Neptune have the lowest eccentricities. They're almost perfect circles. The Earth is still pretty circular in orbit. Okay, Mercury and Pluto's eccentricity actually means that due to Kepler's second law, that it's going to slow down and speed up at different points. Okay, Kepler's laws were developed before Newton's law of universal gravitation. Think of Newton's law of universal gravitation. It says for every object is gravitationally attracted to everything else. Kepler created his laws before Newton created his. So again, according to Kepler's second law, what this means is that these areas A1 and A2 are equal. So this is a very highly eccentric orbit. But what that means is over at A1, when the object is close to the sun that it's orbiting, it has to cover a greater area, a greater angle here to get the same amount of area in this triangle as A2. Okay, because these areas are the same. But because the areas are the same, they actually go faster when it's closer to the sun because it has to cover a greater area than when it's farther away. It doesn't have to cover as much. Okay, we are actually closest to our sun in like December and January, and we're farthest away in June and July. So So that's Kepler's second law. equal areas and equal times, but the closer you are to the planet in your orbit, the faster you're going. The farther you are in your orbit, the slower you're going. Okay. So Kepler's third law is this ratio between the orbital period, the time it takes to go around, and the radius of the orbit. Okay, and we have this thing called the constant of proportionality is this thing, where m is the mass of the object being orbited. So Kepler's third law can be rearranged like this. We're not going to have you do that per se, but we want you to know these two formulas. Okay, that the period is equal to 2 pi times the radius of the orbits cubed divided by the gravitational constant and the mass of what it's orbiting. And the speed of the orbit is the gravitational constant times the mass of what it's orbiting divided by the radius. Okay? Yeah, is the object that is being orbited. Okay, the mass of whatever's orbiting doesn't matter at all. Okay, and this is a big thing. The radius is the distance between the centers of the two objects, not the surfaces, the centers, the middles of the two objects. Okay, so here's some planetary data, some interesting information on the star and the planets of our solar system. Okay, the masses, the radii, and the mean distance from the sun. Okay, we could use these to figure out the orbital periods and the orbital speeds. So we're going to do a problem here to show you how this works. So we're going to look at the orbit of Magellan going around Venus. So Magellan traveled at an altitude of 361 kilometers. If the orbit had been circular, what would Magellan's period and speed have been? All right, so we know the orbit. The radius is 361 kilometers, which is 3.61 times 10 to the 5th meters. What we don't know is the period and the orbital velocity. Okay, so we have to use these equations to solve for that information, to solve for our period and our tangential velocity. Okay, so we're going to use the radius of Venus is 6.05 times 10 to the 6th. The mass of Venus is 4.87 times 10 to the 24th kilograms. Using this. Okay. So we know then that the radius of Magellan is actually the altitude plus the radius of Venus gives us the radius of the orbit. Okay, so then to calculate it, we put it into this long big equation here. We know the radius now is the sum of the radius of the planet and the orbit, gravitational constant, and the mass. So we take that, square it, times 2 pi, and we get that it actually has an orbital period of 5.66 times 10 to the 3rd seconds. So 56,600 seconds. Okay. So then when we have, with this information, we can use this to find the tangential speed. We know the gravitational constant, we know the mass, and we know the radius, which is the orbit, again, the orbital radius. Solve that, we get 7.12 times 10 to the 3rd meters per second. So this is how you solve these types of problems. There's going to be a sample problem on your assessment, on the video assessment. Okay, so it takes about 94 minutes to complete an orbit. Okay, and that is the video for this particular lesson. Look it over again. Okay, if you have any questions, ask, and be sure to fill in your formative assessment. Thank you very much.